Hello everyone. We are looking at the 2.14 atomic emission spectroscopy spectroscopy lab. So let's go ahead and let's discuss the results and just a little more. So in this lab, it was a virtual lab, and you should have read the background info. So we know that Bohr, right, he discovered for hydrogen that those electrons, he thought they were in circular paths or orbits, hence the orbital model. So as a result of that, each energy level has a fixed amount of energy. So you can kind of see here by the rungs, if you think about it, rungs on a ladder, right? There's fixed, distinct amounts of energy, and hence why his model thought the electron would go up and then fall back and release that energy in distinct fixed amounts. Okay, so this is what we have for Bohr's model. Then we have the white light, right? So white light is that continuous spectrum. So like light bulbs, the sun, we look at, when it gives off light. But these spectrums, when we look at these spectrums, we're looking at a specific element, right? And then it will always give this spectrum, and it's like a fingerprint. And we call it the atomic emission spectrum or emission line spectrum. Okay, so we also need to make sure we remember that when we look at this spectrum, that's the visible light range. Okay, there's other energies given off that aren't within our visible light range. So what you should have done was gone ahead and clicked on your lab and gone through. It has some information at the front, and then filled in your answer key. So go ahead, you can pause the video right now. If you need, do a double check and check your answers there. The grading part will get completed. I haven't finished all that yet, but you'll go ahead and update your lab, whatever mistakes you made, resubmit, and then you'll put the keyword, whatever the keyword is, at the end of this video. Okay, so I want to go ahead and look at a few other things before we start looking at the questions. So on your lab, it talked about, and if you've done any research on the internet, you'll see this a lot. You have your continuous spectrum, right? So that's a solid, liquid, gas under those specific conditions, and it's just one continuous spectrum. You have this dark line spectrum here, so it's produced when a cooler gas lies in between the observer and the object emitting the continuous spectrum. And then we have our bright line, which is what we looked at, right? So you have that when the gas, is emitting. So, and then down here were your test. I love this visual, so I wanted to show it to you. Hydrogen atom with excited electron in the third energy shell. And then notice it gets excited, and then it emits that photon, right, that energy, and then it falls back down to a lower energy level. So I just like this visual here of, kind of visualizing that energy, even though the energy has no mass, remember, leaving in that wavelength. So here's just a, 2-minute tutorial that I want to watch. It does a good job of showing us how that energy is going into those different levels, those sub-levels. Energy levels.
A discharge tube is filled with hydrogen gas. When a high voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra.
Okay, so I paused it here for a second because I want you to think before you actually see this. So we have these different energy levels here, and then we have our corresponding wavelengths here. If you recall, we had one hydrogen. It was like in the red region, I believe, the red-orangish region. So first, think, is that going to be 400, 700 nanometers? So remember, shorter wavelength up here, but that means higher frequency, right? Because they're going to be closer together. So higher frequency, higher energy. So this would be the purple region, purple-blue up here, right? And then as we go down here would be our red-orange. So, if we have a line somewhere right in here, where do you think that energy is going? Which, if you had to guess, would that be a 2 to 3 drop? Will that be a 6 to 2 drop? We're talking about energies right down in here. So think about that first, how these the change in the energy levels correspond here to the wavelength, or the energy, the frequency. So would it be a 2 to 3 drop, or would it be a 6 to 2 drop? Hopefully you thought, well, it would be a 2 to 3 drop, right? It's a smaller drop, smaller change in energy levels, therefore less energy, smaller or larger wavelength, smaller frequency. All right, so let's go ahead and see if we were correct.
For the observed line spectrum. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
All right, so we were right. We went from 3 to 2, which gave us right about there. All right, awesome. Hopefully that visual helps too. All right, so back to our answer key. All right, so this is an important one. We need to know why we see those different colors in terms of electrons and energies. So if you didn't get all the credit on here, you need to talk about it in terms of electrons and energies, why we see those different colors for different elements. So those electrons gain that energy, they become excited, right? They jump to those energy levels. Then when they emit that energy, when they fall back down, they'll emit that energy in the form of light or other electromagnetic radiation that we don't see. So depending on what energy level they start at, which we just saw, right? Start at, a 2 and it jumped way up, and they fall back down, it will emit that energy, specific amount, which then will correlate to a specific wavelength. So we see that energy, and depending on the wavelength, that gives us the color. And for each element, they each have their own specific emission spectrum, right? It's like that fingerprint. Okay, so coming down here then for the second part, looking at the emission spectrums, you should have just snapshot, said the color observed, and then put in a snapshot of the actual atomic emission spectrum. So go through and you can see the different ones. So explain why we have that black area. That black area is where the wavelengths are not emitted, right, by the electron. So we only see the light where that electron emits that specific energy that correlates to the wavelength that is within our visible region. Why do we see some lines of light? So the wavelengths of the energy has to be within our visible region. So that's what we actually see. And then, oh, I think I must have miscopied that. I apologize. Let me correct that real quick. All right, here we go. So what does each line of the spectrum represent? That represents the energy of a photon. That's really important to make sure we understand that concept and the definition, what a photon is. Excuse me. Okay, so down here, you can go ahead and look at the answer key here. Check your answer, make any corrections that you need. And then the last question, how could a scientist use an atomic emission spectrum to determine an unknown compound in outer space? Well, we've already talked. each of those atomic emission spectrums are fingerprints, right? They're individual for each element. So they're unique. So we could collect samples, analyze those atomic emission spectrums, and compare it and figure out what element or what elements are actually out there in outer space. Okay, so hopefully that helps. Again, go through, make your corrections, resubmit. The keyword on this, let's see, is going to be right there. So keyword, any questions, let me know. Awesome job.